300,000 kilometers per second. That is the speed of light. The fastest speed possible in our universe. The ultimate limit that nothing, no object, no information, no signal of any kind can ever exceed. This is not a technological barrier. This is not an engineering challenge. This is the fundamental structure of reality itself, and it breaks everything we dream about interstellar travel. For a century, we have known this limit exists. Einstein revealed it in 1905, and every experiment since has confirmed it. Particle accelerators have pushed protons to 99.999% of light speed, spending enormous energy for each additional 9. The limit holds. It always holds. It will always hold. We imagine starships accelerating to light speed, streaking between stars in moments, crossing galaxies in lifetimes. Science fiction has trained us to expect this. Warp drives, hyperspace, jump gates, 1,000 inventions that let our heroes cross the cosmos as easily as we cross oceans. But these are fantasies. They violate the laws of physics in ways that cannot be overcome. The truth is harder to accept but more profound. The speed of light is not just a speed limit like a number on a highway sign. It is the speed at which causality propagates. It is the speed at which cause connects to effect. It is the structural constant around which space-time itself is built. Brian Greene has spent his career exploring the deepest questions of physics. He has written books explaining relativity, quantum mechanics, string theory, the fundamental nature of space and time, and he has been clear about one thing above all others. The speed of light is not a barrier to be broken. It is the speed at which causality itself propagates through the universe. Let me show you why light speed travel is not just difficult but impossible. Let me explain what happens to physics when you try to reach it. Let me demonstrate why the dreams of faster than light travel are not waiting for better technology but are forbidden by the structure of reality. This is the truth about light speed, and it breaks everything. Einstein discovered the speed of light limit in 1905. In his paper on special relativity. It was not an assumption he made arbitrarily. It emerged from two simple premises that had overwhelming experimental support. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light is the same for all observers regardless of their motion. These premises seem innocuous. They seem like reasonable assumptions about how the universe works. But when you follow their logical implications, reality shatters and reforms into something strange. Time becomes relative. Space becomes relative. Mass becomes relative. And the speed of light becomes absolute, the one constant in a universe where everything else depends on your perspective. Let me explain what happens when you try to accelerate toward light speed. This is where physics becomes counterintuitive, where everyday experience fails completely, where the universe reveals its true nature. As an object accelerates, its kinetic energy increases. At low speeds, this relationship is simple. Double the speed, quadruple the energy. This is Newtonian physics, good enough for cars and airplanes and even spacecraft at ordinary velocities. But as speeds approach a significant fraction of light speed, something else happens. Relativistic effects emerge. The object's effective mass begins to increase. Not its rest mass, the mass it has when stationary, but its relativistic mass, the resistance it offers to further acceleration. The faster it goes, the harder it becomes to accelerate further. At 50% of light speed, the relativistic mass has increased by about 15%. Noticeable but not dramatic. At 90% of light speed, the mass has more than doubled. At 99%, it has increased by a factor of about 7. At 99.9%, by a factor of about 22. Let me make this concrete. If your spacecraft has engines capable of producing 1 million newtons of thrust, at rest, that thrust would accelerate you at a certain rate. But at 90% of light speed, the same thrust produces less than half the acceleration, because your effective mass has more than doubled. At 99%, less than 1/7. At 99.9%, less than 1/22nd. The engines have not weakened. The physics has changed. The universe responds to your velocity by making you harder to accelerate. The faster you go, the more the universe resists. This is not a technological problem to be solved. This is how space-time works. The pattern is clear. As you approach light speed, your effective mass approaches infinity, and accelerating an infinite mass requires infinite energy. Infinity is not a number you can reach. It is not a budget you can afford. It is the universe saying no, absolutely and forever. Brian Greene has explained this with an analogy. Imagine pushing a boulder up a hill. At first, it is hard but manageable. As the hill steepens, it becomes harder. Now imagine the hill becomes vertical. Now imagine it curves past vertical, leaning back toward you. No matter how hard you push, you cannot make progress. The geometry defeats the approach to light speed is like that impossible hill. The closer you get, the steeper the energy requirement becomes. At light speed itself, the hill is infinitely steep. You cannot climb it. Not with more powerful engines, not with better technology, not with any amount of energy that could ever exist. Let me put numbers on this. Consider a spacecraft with a rest mass of 1,000 metric tons, about the mass of the International Space Station. How much energy would it take to accelerate this spacecraft to various fractions of light speed? The formula for kinetic energy at relativistic speeds is more complex than the familiar one, half mv squared. It involves the Lorentz factor, a quantity that approaches infinity as velocity approaches light speed. This Lorentz factor is why the energy requirements become impossible. To reach 10% of light speed requires about 450 petajoules of energy. A petajoule is a quadrillion joules for reference. The entire United States consumes about 100 exajoules of energy per year, or 100,000 petajoules. So reaching 10% of light speed requires about 0.5% of America's annual energy consumption. This sounds almost achievable. A massive project, certainly, but perhaps within reach of a very advanced civilization. 10% of light speed would allow a journey to Proxima Centauri in about 40 years. Challenging but conceivable. The numbers suggest possibility, but the numbers escalate rapidly. The Lorentz factor ensures that each additional fraction of light speed costs more than the last. The relationship is not linear. It is not even polynomial. It is asymptotic, approaching infinity. This sounds almost achievable. A massive project, certainly, but perhaps within reach of a very advanced civilization. But the numbers escalate rapidly. To reach 50% of light speed requires about 15,000 petajoules. That is about 2 months of total U.S. energy consumption. To reach 90% requires about 100,000 petajoules, roughly a year of U.S. energy consumption. To reach 99% requires about 700,000 petajoules, about 7 years of U.S. energy. And to reach 99.9% of light speed requires about 2 million petajoules. That is 20 years of total United States energy consumption, just to accelerate one spacecraft. Not to mention deceleration at the destination, which would require similar energy again. But even this astronomical energy expenditure does not get you to light speed. It gets you to 99.9%. To reach 99.99% would require even more. To reach 99.999%. More still, the energy requirement approaches infinity asymptotically. You can get arbitrarily close to light speed with arbitrarily large energy expenditure, but you can never reach it. Brian Greene emphasizes that this is not a technological limitation. Technology works within the laws of physics. It cannot violate them. The speed of light limit is not like the sound barrier. which was once thought unbreakable but yielded to clever engineering. The speed of light is woven into the structure of space-time itself. Breaking the sound barrier required understanding aerodynamics and building engines powerful enough to overcome air resistance at high speeds. The barrier was a practical challenge, not a fundamental limit. Aircraft that break the sound barrier do not violate any law of physics, they just push through a region of difficult aerodynamics. The speed of light is fundamentally different. It is not a region of difficult physics to push through. It is the edge of what physics allows. Beyond it lies not difficult territory but impossible territory, a realm where causality breaks down, where effects precede causes, where the universe ceases to make logical sense. Let me explain why faster than light travel would break causality. This is the deepest reason why it is impossible, more fundamental even than the energy requirements. Causality is the principle that causes precede their effects. This seems obvious. You throw a ball, then it breaks a window. You flip a switch, then the light turns on. The cause always comes before the effect. This order is fundamental to how we understand the universe. But in special relativity, something strange happens. The order of events can depend on the observer's motion. This sounds strange, but it is experimentally verified. Two events that seem simultaneous to one observer might seem sequential to another observer moving at high speed. The event that seems to happen first can differ depending on who is watching. Consider two events: a flash of light in New York and a flash of light in London, occurring at what one observer judges to be exactly the same moment. For an observer traveling at high speed from New York toward London, the London flash happens first. For an observer traveling from London toward New York, the New York flash happens first. This is not an illusion or a measurement error. It is how space-time actually works. There is no absolute simultaneity, no universal now that all observers agree on. Each observer has their own definition of simultaneous events, and these definitions are equally valid. For events that are causally connected, where one event causes the other, all observers agree on the order. The cause always precedes the effect. This is because causally connected events can only influence each other at light speed or slower. The geometry of space-time ensures that causes precede effects for all observers. But if faster than light travel were possible, this protection would fail. An event that is an effect for one observer could be a cause for another observer. You could, in principle, receive a message before it was sent. You could know the outcome of an event before it happened. You could travel back in time. This is not speculation. This is mathematics. If you can travel faster than light in any reference frame, then by switching between reference frames, you can construct a closed loop in time. You can send information to your own past. You can create paradoxes that logic itself forbids. Brian Greene has explained the grandfather paradox in this context. If you could travel faster than light, you could in principle travel back in time. You could prevent your own birth. But if you were never born, you could not travel back to prevent your birth. The logic collapses. The universe cannot accommodate such contradictions. The grandfather paradox is the most famous, but there are others. You could send yourself a message before you sent it. You could bet on a horse race after knowing the results. You could prevent crimes before they happened, but then they would not happen, so there would be nothing to prevent. These paradoxes are not just philosophical puzzles. They represent genuine logical contradictions that the universe seems to forbid. Physics appears to be constructed to prevent them. The speed of light limit is part of this construction. Some physicists have explored whether paradoxes might resolve themselves. Perhaps the universe only allows self-consistent loops, where any time travel that would create a paradox is somehow prevented. This is the Novikov self-consistency principle, named after physicist Igor Novikov, but the Novikov principle does not provide a mechanism for faster than light travel. It only speculates about what might happen if such travel were possible. The fundamental question remains, can you travel faster than light? The answer from physics is no. Some suggest that paradoxes might be resolved by alternative physics, by multiple timelines or self-consistent loops. These are interesting theoretical explorations, but they do not provide a mechanism for faster than light travel. They only speculate about what might happen if such travel were possible. The fundamental barrier remains. The universe appears to be structured to prevent faster than light travel precisely because it would break causality. The speed of light limit is not arbitrary. It is necessary for the universe to be logically consistent. It is the price of having causes precede effects. Let me address the proposed workarounds that science fiction loves to invoke. Warp drives, wormholes, hyperspace. These concepts appear in countless stories as solutions to the light speed limit. Brian Greene has examined each of them seriously. None of them works. The warp drive concept, popularized by Star Trek, proposes contracting space in front of a spacecraft and expanding it behind. The spacecraft itself does not move faster than light. Space itself moves, carrying the spacecraft along. The idea was given mathematical form by physicist Miguel Alcubierre in 1994. The Alcubierre metric is a genuine solution to Einstein's field equations. It describes a bubble of distorted spacetime that could carry a spacecraft at effectively superluminal speeds. Within the bubble, the spacecraft experiences no acceleration, no time dilation, no relativistic effects. It simply sits in flat spacetime while the bubble moves. This sounds like exactly what we want. The mathematics works. The concept is elegant. Physicists have written hundreds of papers exploring its properties. It seems like a loophole in the light speed limit. The Alcubierre metric describes a spacetime geometry that could, in principle, allow faster than light travel without local violation of the speed limit. The spacecraft travels through normal space at normal speeds. The space around it is what moves. It sounds elegant. It is not possible. The Alcubierre drive requires exotic matter with negative mass or negative energy density. Such matter has never been observed. It might not exist. Every particle ever detected has positive mass and positive energy. Negative mass would have bizarre properties, repelling rather than attracting gravitationally. We have no evidence it can exist. Even if exotic matter existed, the quantities required are staggering. Early calculations suggested you would need more exotic matter than the mass of Jupiter. Later refinements reduced this to perhaps the mass of a small planet. Still impossibly large. Recent work suggests even this might be optimistic. The energy requirements, even if exotic matter existed, would be astronomical, perhaps more than the mass energy of visible galaxies. Furthermore, analysis has shown that the Alcubierre drive would still violate causality. Even though the local speed limit is respected, the global effect is the same as faster than light travel. The causality problems remain. You could still construct time loops and create paradoxes, and there are practical problems beyond the theoretical ones. The warp bubble, once created, could not be steered. Signals cannot travel faster than light, so you cannot send instructions to the bubble from inside. Anything in front of the bubble would be destroyed by accumulated radiation and particles. The destination would be obliterated upon arrival. Wormholes are another proposed solution. A wormhole would be a shortcut through space-time, connecting two distant points directly. You would not travel faster than light through space. You would take a shorter path through a higher dimension. The concept of wormholes emerged from Einstein's general relativity in the 1930s. Einstein and his collaborator Nathan Rosen discovered that the equations permitted connections between distant regions of spacetime. These Einstein-Rosen bridges, as they were called, seem to offer a way around the light speed limit. Wormholes are mathematically valid solutions to Einstein's field equations. They can exist on paper. Whether they can exist in reality is another question, and even if they could exist, keeping them open would require exotic matter. The same exotic matter that the Alcubierre drive needs, matter that might be physically impossible. The geometry of a wormhole is fascinating. Imagine folding a piece of paper so that two distant points touch. The paper itself represents three-dimensional space, and the fold represents a shortcut through a higher dimension. A wormhole would connect the touching points, allowing instantaneous travel between them. But the analogy hides the difficulties. The paper folds easily. Space-time does not. To create a wormhole, you would need to distort space-time so severely that it forms a tunnel. This distortion requires energy, enormous amounts of energy, and specifically requires the exotic matter with negative mass density. Natural wormholes, if they form at all, would be microscopically small and would collapse almost instantly. To create a traversable wormhole large enough for a spacecraft would require more energy than stars produce. To hold it open would require negative mass threading the wormhole throat. We have no evidence such mass exists. Physicist Kip Thorne studied traversable wormholes extensively in the 1980s. He was motivated by Carl Sagan, who wanted a scientifically plausible method of interstellar travel for his novel Contact. Thorne found that traversable wormholes were mathematically possible, but required conditions that might never be achievable. The exotic matter problem is particularly severe for wormholes. The negative mass must be precisely arranged in the wormhole throat to prevent collapse. Any deviation would cause the wormhole to pinch off, trapping or destroying anything inside. The precision required is beyond anything we know how to achieve. Brian Greene has been clear about wormholes. They are fascinating as mathematical objects. They illuminate the structure of general relativity. They are excellent tools for theoretical exploration. They are not a practical method for interstellar travel. The gap between mathematical possibility and physical realizability is vast. Hyperspace, the extra-dimensional realm that science fiction spacecraft traverse, is pure fantasy. There is no hyperspace. Higher dimensions may exist in theories like string theory, but they are not accessible realms we can travel through. They are curled up at scales far smaller than atoms, inaccessible to any macroscopic object. String theory proposes that the universe has 10 or 11 dimensions, but 6 or 7 of them are compactified, curled up at the Planck scale, about 10 to the minus 35 meters. You cannot travel through dimensions that are smaller than atoms. You cannot even detect them except through subtle effects on particle physics. Science fiction often imagines that advanced technology could somehow unfold these dimensions, creating pathways through higher dimensional space. This is speculation with no basis in physics. The compactification of extra dimensions, if it exists, is a property of space-time itself, not a configuration that technology can alter. Other science fiction proposes alternate universes, parallel dimensions where the rules are different. Perhaps in another universe, the light speed limit does not apply. Perhaps we could jump there, travel vast distances, and jump back. But we have no evidence that alternate universes exist. We have no mechanism for traveling between them if they do. And even if we could reach another universe, there is no reason to think the light speed limit would be different there. The limit appears to be a consequence of fundamental principles that would apply in any logically consistent universe. Every proposed workaround to the light speed limit fails. They fail theoretically, requiring conditions that physics may forbid. They fail practically, requiring energy that does not exist. They fail causally, creating paradoxes that logic cannot accommodate. The speed of light limit stands unbreached. Let me discuss what light speed travel would mean, even if it were possible. Even setting aside the impossibility, even granting science fiction its assumptions. Lightspeed travel would still break everything. Time dilation is one of the strangest consequences of special relativity. As you approach light speed, time slows down for you relative to stationary observers. At 90% of light speed, time passes about 2.3 times slower for you than for someone at rest. At 99%, about 7 times slower. At 99.9%, about 22 times slower. This is not an illusion. This is not a measurement artifact. This is how time actually works. Experiments with precise atomic clocks on aircraft have confirmed time dilation at everyday speeds. Particle accelerators confirm it at speeds approaching light. GPS satellites must account for it to function accurately. At light speed, time dilation becomes infinite. From the perspective of a photon, no time passes during its journey. A photon emitted from a star 4 light-years away arrives at Earth having experienced zero elapsed time. From the photon's perspective, emission and absorption are simultaneous. This is difficult to comprehend because photons do not have a valid reference frame in the usual sense. Asking what a photon experiences is not quite a well-formed question, but the mathematics points towards zero elapsed proper time, a journey of any distance occurring instantaneously from the traveler's perspective. For a massive object traveling at light speed, the same would apply. The journey would be instantaneous from the traveler's perspective, but the destination would experience the full elapsed time. You would arrive in the future, not just the future of your departure point, but a future that has lived without you for as long as your journey took in external time. At light speed, length contraction also becomes infinite. From the traveler's perspective, the entire journey would be compressed to zero length. You would not travel through space. You would simply appear at your destination, the intervening space having contracted to nothing. Brian Greene finds these implications fascinating as thought experiments. They reveal the strange geometry of space-time, the counterintuitive nature of reality at extreme speeds. But they also reveal why light-speed travel is impossible. At light speed, the physics becomes singular. The mathematics divides by zero. The universe says no. There is one more aspect of light-speed travel I want to address. The energy required to reach it would, if somehow achieved, have catastrophic consequences. We have discussed the energy required to accelerate to high fractions of light speed. But that energy does not disappear. It becomes kinetic energy of the spacecraft, and kinetic energy can be released destructively. The kinetic energy of an object increases with velocity. At relativistic speeds, this energy becomes enormous. A spacecraft traveling at 99% of light speed would have kinetic energy equivalent to about 7 times its rest mass energy. E equals mc squared tells us that this is an enormous amount of energy. Let me translate this into familiar terms. The rest mass energy of 1 kilogram is about 90 petajoules, equivalent to about 20 megatons of TNT. A 1,000-ton spacecraft at 99% of light speed would carry kinetic energy equivalent to about 600 megatons of TNT. A 1,000-ton spacecraft at 99% of light speed would carry kinetic energy equivalent to about 600 megatons of TNT. That is more than 10 times the largest nuclear weapon ever detonated. Impact with any object, even a small asteroid, would release this energy explosively. This makes relativistic spacecraft extraordinarily dangerous. They are weapons simply by virtue of their motion. Any impact would be catastrophic. The destination would need to be approached with extreme caution, decelerating far from any object to avoid devastating collisions. At light speed itself, the kinetic energy would be infinite. The spacecraft would be a universe-destroying weapon, capable of releasing infinite energy upon impact. Obviously, this is impossible. The impossibility of infinite energy is another way the universe forbids light-speed travel. The energy problem cuts both ways. You need enormous energy to reach relativistic speeds, and having reached them, You carry enormous destructive potential. The universe seems structured to make relativistic travel both impossible to achieve and dangerous if achieved. This is what Brian Greene means when he says, light speed travel breaks everything. It breaks energy budgets. It breaks causality. It breaks the mathematics of physics itself. The universe is structured to prevent it, not as an arbitrary rule, but as a necessary condition for reality to be coherent. What does this mean for interstellar travel? It means that crossing the distances between stars will take time, real time measured in years or decades or centuries. It means that travelers will age during their journeys. It means that Earth will continue without them while they travel. This has profound consequences for any interstellar mission. The travelers depart. They experience their journey, they arrive, but far more time has passed on Earth. Their friends and family have aged. Civilizations may have changed. The Earth they return to, if they return, will not be the Earth they left. At 90% of light speed, a journey to Proxima Centauri would take about 4.7 years of Earth time. The travelers would experience about 2 years due to time dilation. This is not instant. This is not easy. But it is possible within physics. It is possible in principle, even if the energy requirements make it practically impossible. A journey to a star 100 light-years away, at 90% of light speed, would take about 111 years of Earth time. The travelers would experience about 48 years. They would return to an Earth where everyone they knew had died, where history had moved on without them for more than a century. This creates a profound asymmetry. The travelers sacrifice connection for destination. They trade their place in Earth's timeline for arrival at a distant star. Even without faster than light travel, relativistic travel severs bonds. The light speed limit ensures that interstellar travel is always a one-way trip through time. Brian Greene has written about this temporal isolation. Even at the fastest speeds physics allows, interstellar travelers become exiles in time. They cannot return to the world they left. They can only arrive at a world that has moved beyond them. But light speed itself remains forbidden, and faster than light remains doubly forbidden. The stars are not unreachable because we lack technology. They are unreachable because the universe is vast, and the speed of light is finite. These are features of reality, not bugs to be fixed. Brian Greene has written about finding wonder in these limits. The speed of light is not a disappointment. It is a revelation. It tells us something profound about the structure of space-time, about the relationship between space and time, about the nature of causality itself. Before Einstein, space and time were thought to be separate, absolute, the stage on which physics played out. Relativity revealed them to be intertwined, relative, dynamic. The speed of light is the conversion factor between space and time, the constant that unites them into space-time. This unity is beautiful. It explains phenomena that were mysterious before. It predicts effects that have been precisely confirmed. It is not a limitation arbitrarily imposed, but a feature of reality that makes sense of the whole. The universe could have been different. It could have allowed infinite speeds. It could have permitted time travel. It could have been a chaotic realm where effects precede causes and logic has no hold. Instead, it is ordered. It is structured. It is comprehensible. The speed of light limit is part of what makes comprehension possible. Consider what the alternative would mean. In a universe without the light speed limit, signals could arrive before they were sent. You could know the future before it happened. Causality would be arbitrary rather than necessary. Science would be impossible because prediction would be meaningless. We live in a universe where causes precede effects, where the future is unknown, where actions have consequences that unfold in time. The speed of light limit protects this order. It ensures that the universe makes sense, that logic applies, that science is possible. This is not a small thing. In a universe without the light speed limit, Physics as we know it could not exist. Prediction would be impossible. Knowledge would be meaningless. The very concepts of cause and effect would dissolve into incoherence. Brian Greene suggests we should be grateful for the light speed limit. It gives us a universe we can understand. It gives us time that flows in one direction. It gives us a cosmos where science can discover truths and technology can build wonders, even if those wonders cannot include faster than light travel. This gratitude is not resignation. It is appreciation. The universe owes us nothing. It could have been incomprehensible, chaotic, hostile to understanding. Instead, it has patterns. It has laws. It has regularities that we can discover and describe. The light speed limit is one of those regularities. Understanding the light speed limit deepens our understanding of everything else. It connects to quantum mechanics through relativistic quantum field theory. It connects to gravity through general relativity. It connects to thermodynamics through the impossibility of perpetual motion. The limit is woven through all of physics. The stars remain distant. The void between them remains vast. Light speed travel remains impossible, and faster than light remains doubly. So this is the final truth about interstellar distance. It cannot be wished away. It cannot be engineered around. It can only be accepted. But acceptance does not mean defeat. The solar system is vast. 8 planets, hundreds of moons, millions of asteroids, billions of comets. All of this is accessible to slower than light travel. All of this awaits human exploration. The light speed limit closes the galaxy to us but leaves us with more than enough. The total surface area of bodies in the solar system exceeds the surface area of Earth many times over. Mars alone has land area equal to Earth's continents. The moons of Jupiter and Saturn offer diverse environments for exploration. The asteroids contain resources beyond counting. Humanity could expand through the solar system for millions of years without exhausting its possibilities. We could build habitats in orbit. We could mine asteroids for metals and minerals. We could establish research stations on every significant body. The light speed limit takes the stars but leaves us with a kingdom. Acceptance is wisdom. Knowing what is impossible focuses energy on what is possible. The solar system remains accessible. Slower than light travel, though challenging, is not forbidden. We can still explore, still discover, still wonder, just not as fast as we dreamed. Look at the stars tonight, beautiful and distant. Know that light from them takes years or centuries or millennia to reach you. Know that you can never travel to them quickly. Know that light speed is the ultimate limit, unbreakable by any technology, fundamental to the structure of reality. When you look at Proxima Centauri, you see it as it was 4 years ago. When you look at the stars in Orion's belt, you see them as they were about 1,000 years ago. When you look at the Andromeda Galaxy, you see it as it was 2.5 million years ago. You are looking back in time. This is the price of the light speed limit. Information cannot travel faster than light. Causality cannot propagate faster than light. We see the universe as it was, not as it is. The present moment for distant objects is unknowable. But this price purchases something valuable. It purchases a coherent universe. It purchases time that flows in one direction. It purchases causality that makes sense. The universe could have been chaos. Instead, it is ordered, and the light speed limit is part of what orders it. And find peace in this knowledge. The universe is what it is. The limits are what they are. Within those limits, wonder still exists. Discovery still beckons. The cosmos still calls, even if it calls us to patience rather than speed. The solar system offers enough exploration for millions of years. Mars, the moons of Jupiter and Saturn, the asteroids, the comets, the distant reaches of the Kuiper Belt. All of this is accessible to slower than light travel. All of this awaits human exploration. We do not need faster than light travel to have a magnificent future. We need only accept that the future will unfold at the pace reality allows. The stars will remain distant, but the solar system is vast. The light speed limit closes the galaxy but opens our cosmic neighborhood. Light speed travel breaks everything. This is the verdict of physics, the conclusion of mathematics, the structure of space-time itself. Brian Greene has shown us why, has led us through the reasoning, has demonstrated the necessity of the limit. This verdict is not a failure of human imagination. Human imagination is magnificent. It has conceived of faster than light travel, has designed warp drives and wormholes, has dreamed of crossing the galaxy. The failure is not in the dreaming but in the believing. The dreams are beautiful. They are not possible. But imagination serves purposes beyond prediction. It entertains. It inspires. It explores what, if scenarios that illuminate what, is reality. Science fiction about faster than light travel teaches us something even when it depicts the impossible. It teaches us what we wish were true, and in that wishing, we learn about ourselves. Brian Greene himself has written about the value of imagination in physics. Thought experiments, hypotheticals, impossible scenarios. These are tools that physicists use to understand reality. Einstein imagined riding a beam of light. That impossible imagining led to relativity. So let us continue imagining faster than light travel in our stories and our dreams. But let us not confuse imagination with expectation. The stories are fiction. The physics is real. The light speed limit holds regardless of what we imagine. The stars are beyond us. Not because we are weak or foolish or unimaginative, but because the universe is built a certain way. The speed of light is finite. Causality must be preserved. Reality must be coherent. These requirements leave no room for faster than light travel. This is the fundamental truth that Brian Greene has spent his career helping people understand. The universe has rules. The rules are not arbitrary. They make the universe coherent, comprehensible, and meaningful. The light speed limit is one of those rules. Every time we discover a rule of physics, we learn something about the nature of reality. The light speed limit tells us that space and time are connected, that causality is fundamental, that the universe has a structure that prevents paradoxes and enables prediction. This knowledge is itself a kind of travel. We cannot physically visit the stars, but we can understand the physics that governs them. We cannot experience time dilation directly at relativistic speeds, but we can calculate its effects precisely. Knowledge is a form of reaching, even when physical travel is impossible. That is the truth about light speed. It breaks everything we dream, but it enables everything we have without the limit. There would be no ordered universe to dream in. That is enough. That is the bargain reality offers. That is home. Brian Greene has written about the beauty of physics, even when physics tells us what we cannot do. The light speed limit is part of that beauty. It is elegant. It is necessary. It emerges from simple principles and has profound consequences. This is what physics does. The dreams of faster than light travel will persist. Science fiction will continue to imagine warp drives in hyperspace and wormholes. These stories serve a purpose. They expand our imagination. They inspire wonder. They let us explore possibilities that reality forbids, but we should not confuse fiction with possibility. The gap between them is not one of time or technology. It is a gap of physics, of mathematics, of the fundamental structure of reality. Faster than light travel is not waiting for better engines. It is forbidden by the universe itself. This knowledge is liberating. Once you accept what is impossible, you can focus on what is possible. The solar system awaits. Slower than light exploration offers challenges enough for millennia. The cosmos is vast, and we have our corner of it. The light speed limit does not diminish us. It defines us. We are beings who evolved under a certain physics, in a certain universe, with certain constraints. These constraints shaped us and continue to shape us. They are not our enemies, but our context. Look at the stars one more time. They are unreachable at faster than light speeds. They are barely reachable at slower speeds. They are beautiful regardless. The light that reaches your eyes has traveled for years or millennia, and it brings information about wonders you can study even if you cannot visit. Every photon that reaches your eye from a distant star has crossed the void at exactly the speed of light. Not faster, not slower, exactly that speed. That constancy is remarkable. That constancy is what makes the universe predictable, comprehensible, and navigable, even if not traversable. The light from Proxima Centauri has traveled for 4.2 years. The light from Betelgeuse has traveled for about 700 years. The light from the Andromeda Galaxy has traveled for 2.5 million years. Each photon brings a message from the past, preserved perfectly across the void. That is enough. That is the universe we have. That is home.